Our today's speaker is Bhishan Jacelon, and he will talk about quantum metric Choquet simplices.
Well, thank you, Karen, and thank you all for coming. So I'm going to tell you about these certain structures that I've been working on lately, some work in progress. You know what, let's just jump right into it. So I want to start with some motivation. Let me explain what this was the title of a talk I gave when I was a postdoc in Toronto some years ago. Before I had sort of fully fleshed out the details that I'm going to tell you about now. But let me explain what exactly I mean by this. So the Highlanders slogan is there can be only one. So this is not a talk about classification, but classification is in the background and it's what's lying behind all of this. And what I mean by there can be only one is, all right, we have this category of nicely behaved C-star algebras, and we have some sort of K-theoretic invariant that classifies things. So if I know what the invariant is, there can be only one isomorphism class of an object that has that as its invariant. But this also works for morphisms. If I sort of enrich my invariant suitably, and I know what this enriched invariant is, then there can be only one approximate unitary equivalence class of a morphism into this nice category of C-star algebras. Okay, so that's what I mean by a Highlander type term. There can be only one. On the other hand, Napoleon says, all right, so any two objects with the same invariant are isomorphic. Flipping that around, you know, if I have two distinct values of invariant, I know I have non-isomorphic objects. But what Napoleon is really saying is that, okay, all objects with the same with unequal non-isomorphic invariants are non-isomorphic, but some are more non-isomorphic than others. Okay, so this is not Napoleon Bonaparte. This is Napoleon from Animal Farm. All animals are equal, some are more equal than others. Anyway, so this is the sort of feeling that I have that I'm not really happy with a binary classification, 0, 1, isomorphic or not. I want a quantized version of this. I want something that captures the notion that if I look at two invariants, yeah, some of them look closer than the others, all right? So I just want to, all of this is about making that kind of feeling precise. So this, what I've written down here is just a little bit more details about what I mean by classification. As I said, it's some K-theoretic based thing. So throughout today's talk, the way I phrased it here, I phrased it in terms of objects or morphisms. I'm just going to talk about objects today, but the same sort of structure I'm going to tell you about can also be adapted to talk about comparing morphisms. Okay, but it's just going to be about objects today. And in other words, the question that I'm asking is, how do I measure distances between two objects in this category of classifiable C-star algebras? And just very quickly, as I said, it's not talking classification, but by classifiable category, I mean the collection of unital, simple separable nuclear set stable UCT C-star algebras, whatever all of that means. As we need whatever terminology, I'll tell you more about it as we go on. Okay, so that's the basic idea of what I'm trying to do. All right, so some terminology before we get going. Throughout, A will be a separable C-star algebra. So you noticed in the title of the talk, it was metric. So I'm talking about metrizable things. So separability is unavoidable. I have to make this assumption. By T of A, I mean the tracial states on A. So the positive linear functionals that satisfy the trace identity. Trace AB is trace BA. By F, you know, this is it's a compact convex set when we equip it with the weak star topology, so the topology of pointwise convergence. And by F of T of A, I mean the continuous affine maps from the trace space to the real numbers. By affine, I just mean it preserves convex combinations. I will denote by a hat this evaluation map. So from the self-adjoint elements to affine functions on the trace space. So A hat is just the evaluation map. A hat of tau is tau of A. The kernel of this evaluation map I denote by A0. You can show it's in this paper of Kuntz and Peterson that it is a closed subspace of ASA. And then finally, I take this quotient of the self-adjoint elements by this kernel of the evaluation map. So in other words, what I'm doing is I'm modding out all of the things that cannot be distinguished by traces. And what I get out of doing this is that the state space of this object is now exactly the trace space of the algebra I started with. Okay, so this is just a sort of technical trick that I do so that when I can speak of states of this object and I know that I'm just talking about the traces of the C-star algebra. Okay, so just a little technical detail that's necessary. I would like this quotient procedure to be well behaved. So if A is a unital C-star algebra and is either simple or it's of the form continuous functions from some compact Hausdorff space into matrices, I mean, it holds more generally than this, but just these are sort of particular interest. Then this quotient is what's called an order unit space. So if you're not familiar with what an order unit space is, I'll just say briefly, it's a vector space with an order structure that's well behaved, okay? It's compatible with the vector space structure, this order structure. And what makes it an order unit space is that I have a distinguished element E that is an order unit in the sense that, so there exists an E such that for every X in my space, there is some real number R bigger than 0 such that I can sandwich X between RE and E, right? So I would like to know that there is such a distinguished element E. I call it the order unit. And in this context, it's just going to be the class of the unit. I just take the unit of the C-star algebra, look at its class and the quotient. That's going to be my order unit, right? And I want it to satisfy this property. And the other property I want is that, you know, if this holds for every R bigger than 0, then X has to be the 0 element. So what this gives me is that it gives me a nice compatible norm that I can put on my order unit space, right? But whatever, just think it's a vector space with a nice order structure, and from that, a nice normed structure, okay? So I'm claiming that this quotient with this order unit you'd expect is indeed an order unit space. So it has the right behavior that it should. Well, actually, I'm really claiming two things here. So A, the self-adjoint part of the C-star algebra has its own order structure. We know C-star algebras have an order structure. And the order structure I would naively put on the quotient is just the quotient order structure. So the positive cone is the image of the positive cone. But what I'm claiming here is, in fact, this naive thing you do to get the positive cone coincides with those elements that evaluate to something non-negative on all traces, okay? All right, whatever. The take-home message is that in the C-star algebras that I care about, this quotient is a nicely behaved structure, nicely behaved order unit space. Yeah, please. Yeah. Yeah, I'm quoting out by nothing because the things that vanish on all traces are states in a commutative C-star algebra, and the only thing that vanishes on all states is the only positive thing that vanishes. Oh, sorry, I've said yeah. Sorry. So if two functions agree on all traces, this means, in other words, that they agree pointwise, which means they are the same element. Yeah. Well, the irreducible, they are the measures in general. The multiplicative traces, the characters are the yeah. So in the commutative case, this A0 is just 0. All right. So yeah. So when I have this nice kind of behavior, I'll just say that AQ is tracially ordered, which is the kind of behavior I want. All right. So finally, let me now tell you what a quantum metric Choquet simplex is, or a C-star algebraic quantum metric Choquet simplex. So it is a C-star algebra, separable unital C-star algebra A, and equipped with a semi-norm on it, which I'm allowing to maybe take the value infinity. And I want some properties to hold. Firstly, I want this nice tracially ordered business. So just think A is simple. If A is simple, this first one is satisfied, okay? Next, I want L to be self-adjoint. So the semi-norm of A star should be the semi-norm of A. I want it to be lower semi-continuous, and I want it to be densely finite. So I'm allowing the value infinity, but on a dense set, I have finite values. The kernel of this L should be everything So in a second here, I will tell you the example to keep in mind. The example to keep in mind, I'll tell you now, in fact, is just continuous functions on some compact metric space. And this L is just the Lipschitz seminorm of a function, okay? Constant functions have Lipschitz constant 0. So I would expect these to be in the kernel of my Lipschitz seminorm, right? So that's so the kernel L has to consist of multiples of the unit. But it's also going to consist of those things that vanish on all traces. So I also want these things to be in the kernel of my seminorm. And the last property that I want is that this seminorm on the algebra is going to induce a metric on the trace space of the algebra, as I've written here in red. So that if I want to know what the distance between two traces are, I just evaluate the supremum of the differences over elements that have Lipschitz seminorm at most 1. And I want this to be the weak star topology. Okay, so this is the structure that I'm interested in, right? So it's a C-star algebra with seminorm. Yep, so let's see that immediately. Okay, so as I said, the example to keep in mind is C of X. And in this case, the two structures are the same. So in the commutative case, it is exactly the same definition as a compact quantum metric space in the sense of refill. So what is new in the non-commutative setting is that firstly, in the compact quantum metric sorry, it's always a tongue twister, these two things. And as you can see, the two acronyms are very, unfortunately, just permutations of each other. So anyway, so what's new is that the kernel of L in the original refill notion would just be the span of the unit. There is none of this A0 business. The A0 business is what's new here. And I'm in, yeah. A0 is just those things that vanish on all traces. Yes, it's the kernel of this. So A0 is just all self-adjoint elements such that trace of A0 for all traces. Yeah. And that's the point is I'm talking about, I want to recover information about the algebra from my trace space. But if elements in my algebra, it cannot be distinguished by traces, I can't do this. So I have to get rid of those things that cannot be distinguished by what's on the traces. And I just get rid of it by quotienting. That's all. So that's the difference. It's just what you should think of morally. It's just the same as Riefel's notion of a compact quantum metric space, except I'm doing it on the trace space. That's all. And I'm just doing whatever technicalities I need to make this sensible. That's all I'm doing. Okay, so as I said, key example, commutative setting, rho is a metric on X, L of F, this seminorm is just the Lipschitz seminorm. So the least thing that works as a Lipschitz constant. All right. What I would like to do now is explain the terminology. So I've called this a quantum metric Choquet simplex. Where is Choquet simplex appearing in any of this? Let me remind you first of all what a Choquet simplex is. So it's a certain kind of a metrizable Choquet simplex. So it's a certain kind of metrizable compact convex subset of a topological vector space. And here's the defining property. I want every point in my set, so every x in k, to be uniquely represented by a Borel probability measure supported on the boundary. What I mean by represented is that if I have some affine functional f and I want to know what f of x is, I just need to integrate it with respect to this measure mu x on the boundary. Okay, so a couple comments here. There always exists, whatever compact convex set K is, there always exists at least one mu x that does this job that's supported on the boundary. This is the theorem of Choquet. So it's really the defining property of a Choquet simplex here is uniqueness of this measure, the uniqueness of this representing measure. So that's the first comment. Second comment is that in finite dimensions, all this is saying is that every point in K can be uniquely expressed as a linear combination, as a complex combination of extremal points. Okay, so what I should think of in finite dimensions, a simplex is what I think a simplex is. So it's a point, a line segment, or a triangle, or a simplex, but it's not a square, for example, because the square I don't have uniqueness. So square, I can write the midpoint as the midpoint of these guys, or the midpoint of these guys. It's a way of making sense of affine independence in infinite dimensions, if you like. Okay, so that is what a Choquet simplex is. And here's the reason for my terminology. So the following equivalent for, let's say I have an order unit space E. So vector space with some nicely behaved order structure, and I have a nicely behaved norm attached to it, and the norm is complete. So the following things are all telling me the same information. So firstly, E is isomorphic to as an order unit space. One of these Kuntz-Petersen quotients. So one of these quotients where I'm looking at a separable universal C-star algebra, I take the self-adjoint elements, I quotient out by this A0 thing, okay? So E is such a, where we're with this tracial ordering, blah, blah, blah. So that's the first condition. The second condition is that E is isomorphic affinely, well, isomorphic is an order unit space to the affine functions on some metrizeable Choquet simplex. And thirdly, is separable and has the Riesz interpolation property, which I've reminded you what that is here in an ordered vector space. If I have two x's below two y's, then I can find some z sandwiched between them. All right. So maybe just a brief comment on why this is true. So why is two the same as three? This is something you can look up in Alfson's convex analysis book. Riesz interpolation characterizes this uniqueness of representing measures. Why does one imply two? So if I am isomorphic to AQ, then the state space of E is, as I said, by design, the trace space of A. Then I have something called if I can remember what it's called, the Cadison representation theorem, which says that a complete order unit space E is isomorphic to affine functions on its state space. So it's affine function. So one implies that E is isomorphic to affine functions on trace of A. But then finally, it's a result that the trace space of any separable unital C-star algebra is a metrizable Choquet simplex. Okay, so that's why one implies two. And as for why two implies one, okay, this is some other argument. The crucial idea is that if you give me a metrizable Choquet simplex, then I can find a simple separable unital C-star algebra, an AF algebra even, that has that Choquet simplex as its trace space. So that's how I recover a C-star algebra if you give me an abstract Choquet simplex. Okay, so that's why I'm calling it a quantum metric Choquet simplex. I have a Choquet simplex, I'm putting some metric on it, and the quantum bit is in Riefel's sense, meaning I'm looking at functions on this structure. So when Riefel is talking about quantum metric spaces, he's talking about spaces of functions on metric spaces. All right. And by the way, so in this definition, I said it was a C-star algebraic quantum metric Choquet simplex. So I've attached it to a C-star algebra. But by this theorem, I could do this all level up in abstraction just by talking about complete order unit spaces and the Riesz interpolation property. But let's stick with C-star algebras, and there's no loss in generality from this theorem. Okay, so let me give you some examples now of this kind of structure. So I already told you the key example to bear in mind is just C of x. C of x with a metric on x and the attached Lipschitz seminorm. I can do a similar procedure to describe for you a variety of examples of these kinds of structures in a analogous sort of way. And these are special examples that I call quantum metric Bauer simplices. So a Bauer simplex is a Choquet simplex where the extremal boundary is closed. So it's a compact set, which is definitely not always the case. So it's something quite special. So for example, the Poulsen simplex, it's well known, the extreme points are dense in the whole simplex. They're very much not closed. Okay, so this kind of structure is going to be just essentially, morally, it's going to be a special case of the quantum Choquet stuff, just requiring that the trace space is Bauer. And I just want everything to be nicely compatible. So yeah, that's the first requirement. The trace space of the C-star algebra is a Bauer simplex. So I have a nice compact boundary. And then, okay, I have some procedure for describing to you this seminorm. And here's what I do. So, okay, I have this space X. This is the boundary of the trace space here. I put metrics, or I start with a metric on this space. Okay, so I'm given. Maybe I'm imagining that the boundary of my trace space is the interval, say 0, 1. So I have the Euclidean metric, say. Now, remember I said the defining property of a Choquet simplex is that I have, for every point, I have a unique representing measure on the boundary. For Bauer simplices, this is a one-to-one affine homeomorphism. Okay, so I can, instead of talking about points in the simplex, I can just talk about measures on the boundary. So if I want to extend my metric from the boundary to the whole trace space, that's all I do. I just need to extend the metric from X, the boundary, to measures on X. Okay, I just need some way of extending the metric. And there are a variety of ways that you can do this. I've gone with the way that's sort of most compatible with the rest of the structure, which is I define the one Wasserstein metric, or it's also called the Kantorowicz-Rubinstein or the Monge-Kantorowicz metric on measures. Okay, so it's similar formula to what I had before. So the Wasserstein distance between two measures, between two points, two traces, sigma and tau. I just evaluate the difference in the integrals with respect to the associated measures over all one Lipschitz functions. Okay, maybe that's a lot to take in, but just the procedure is start with a metric on the boundary, extend it somehow to a metric on measures, and that gives me a metric on the whole trace space because it's a Bauer simplex. And then ultimately what I want is to define a Lipschitz seminorm on the algebra, and I just do that by essentially what I've written here in red at the very bottom. So if I want to know what the seminorm of a self-adjoint element A is, I just think of A as a function on the trace space, this hat. Remember, hat was just is this evaluation map. So every A gives me this A hat, which is just honest to goodness affine functional on the trace space. And I just compute the Lipschitz seminorm of that continuous function with respect to this metric that I've defined. Okay? So these examples are, I just start with the Bauer simplex and a metric, and I just sort of bootstrap up to get a Lipschitz seminorm on the algebra. This gives me a procedure of putting this kind of structure on lots and lots of examples. So C of X works this way, or more generally, C of X continuous functions from X into matrices, for example, or nice subalgebras like the dimension drop algebras that I wrote here at the bottom. So these are continuous functions from the interval into matrices with some boundary conditions. But this, I also get, so for example, in this ZPQ here, the trace space is measures on 0, 1. The boundary of the trace space of ZPQ is 0, 1 itself. That's why it's a Bauer simplex. It's a general fact. So the boundary of the trace space of C of X or something C of X like this is just X. That's why it's a sort of motivating example. Okay, so on examples like this, I have a way of defining these quantometric, specifically Bauer simplex structures. One thing about these examples I've written at the bottom here, they're not simple, but you can, in fact, get lots of simple examples, lots of classifiable examples, in fact. So here's a theorem that I'm telling you. So you give me a compact connected Riemannian manifold with its intrinsic metric, meaning rho, the distance between 2 points is the infimum of the length of paths between the points. Then I can give you a projection S, classifiable C-star algebra ZX that further has this structure of a quantum metric Bauer simplex. So it's equipped with some seminorm L that is constructed in the way I described in the previous slide. And then the boundary of the trace space of this algebra is the X that I started with. So this is a unital C-star algebra. So when I say projectionless, I mean no non-trivial projections apart from 0 or 1. Okay, so this gives you a way of getting lots and lots of nice model examples. Let me give you a quick idea of how you construct these algebras, just so it's not so mysterious what I'm talking about here. I've called these model algebras ZX because it is a Jiangsu-like construction. So I think of these as kind of high dimensional Riemannian Jiangsu algebras in a sense. Let me tell you how I build them. So I build them up as an inductive limit of things, of blocks which I'm calling X, Pn, Qn. Pn and Qn are some co-prime natural numbers, and these phi n's are some connecting maps from one block to the next. These XPQs are like the dimension drops that I had on the previous slide, except instead of the interval 0, 1, I have this space X. So X is this compact connected Riemannian manifold I started with. But it's the same thing. Instead of the boundary points 0 and 1, I just choose two base points, x0 and x1, and I have the same boundary conditions, if you like. So this is what XPQ is. It's called a generalized dimension drop algebra. And these connecting maps from one stage to the next, they are just given by, okay, so modulo conjugation by some unitary to get the boundary conditions satisfied correctly. It's just, I send F to the diagonal matrix where it's F composed with some functions, psi1. So these psi i's are just functions from X to X. And in fact, even more specifically, they are all of this form. So the vast majority of the psi i's are just the identity map on X. Most of what's left are just constant maps. And whatever is left are at least Lipschitz. Okay, so the fact that I just have here a little picture of describing each case. So this is where X is the interval. So this is the identity map. This is a constant map. And this is some one, in fact, in this case, it's one Lipschitz. And all right, the fact that most of these are the identity is what's telling me that in the limit, I get the right trace space. The fact, what are these constant maps doing? I'm just varying them densely over the space, so I get something simple in the limit. And the fact that everything that's left is Lipschitz is that, so one of the conditions in my structure of a quantum metric Choquet simplex was that elements with finite seminorm should be dense. So the Lipschitz functions, the tracially Lipschitz functions should be dense. And so I want to choose my maps, my connecting maps carefully so that Lipschitz functions get sent to Lipschitz functions. Because otherwise, the Lipschitz seminorms could be blowing up, and I get something very non-Lipschitz in the limit. Okay, and in fact, this right here is the only place where I'm using this manifold structure. So if I cross out the word projectionless, this works for any compact connected space X. And it's much more simply. So all of this sort of dancing around with dimension drop type things is really to get projectionless. But if I don't care about that, things become much easier. And where am I using Riemannian manifold? Well, okay, without sort of getting too much into the details, at some points in the argument, I want to build connecting maps between 2 points. I want to build, in fact, a bi-Lipschitz path between 2 points. In a Riemannian manifold, I sort of have enough room to manipulate things locally and have GD6 and blah, blah, blah. And so I can show that there is a bi-Lipschitz path that I want. But I think this should be true more generally, probably in the setting of what are called complete length metric spaces. Okay, but anyway, so that's how I build these Jiangsu-like models, and they are all examples of my my structure of interest. All right, so finally, well, not finally. I mean, I have a few more slides left, but right, let's just pause and check in. What am I trying to do here? So I said I wanted to make sense of the distance between classifiable C-star algebras. And I'm building this additional structure on certain nice classifiable C-star algebras in order to make sense of this. So now I've sort of given you an indication of what that extra structure is on the algebra. Now let me tell you about what I'm proposing as my distance between objects. And I'm just going to use Riefel's notion of a quantum Gromov-Hausdorff distance between two compact quantum metric spaces. So E1 and E2 here are these order unit space structures. L1 and L2 are these seminorms. And if you know how the Gromov-Hausdorff distance is defined between two compact metric spaces here, I just look at the Hausdorff distance between the images of embeddings of my two spaces into a third space here, and I take the infimum over all embeddings. I'm just doing a similar, or Riefel is doing a similar thing here in his context. So if you give me two of these order unit space guys, or just think these C-star algebras equipped with these semi-norms, giving me these metrics on the trace spaces here. I just do the same thing. So I look at the state spaces of my order unit spaces or the trace spaces of my C-star algebras, and I look at all ways of isometrically and affinely, just remembering that these are affine, these are convex structures. So isometric affine embeddings of my trace spaces into some third trace space. Okay, and I look at the Hausdorff distance between these two images, and I take an infimum. Right, so this is Rieffel's notion of the quantum Gromov-Hausdorff distance. So distance 0 is equivalent to the two structures being isometric in a suitable sense, which I will not get into, but you can make sense of the notion of an isometry. Essentially just an isomorphism between the two E's that's compatible with the L's, as you might expect. Okay. So that's my notion of distance that I'm going to be playing around with. One thing I'll tell you, so you can ask about this blackboard bold QMBS is the metric space of isometry classes of quantum metric Bauer simplices equipped with this quantum Gromov-Hausdorff distance. And I'm claiming to you that this is a closed, hence complete subset of the wider space of compact quantum metric spaces with the same distance. Yeah, so I mean, I was originally trying to prove this not for the special Bauer simplices examples, but more broadly for the Choquet simplices. But I could not. But I at least managed to I think, show that QMBS is closed. And then once you know that it's complete, you also have a characterization of when collections of substructures are compact and so on. Okay, but anyway, what I would like to do next is, all right, so I described for you some procedure of constructing examples, but they are specially these Bauer simplex examples. So I do it in a special way of putting a metric on the boundary, extending to measures, bootstrapping up. But now I want to tell you, all right, how do I get structures that are not Bauer simplices potentially? And I'm going to do this by taking cross products in a suitable sense. So first, let me introduce to you what I'm calling a quantum system associated to a topological dynamical system. So topological dynamical system means, as I have here, I have let's say some compact factorizable space X, and H is some continuous map from X to X, or often a homeomorphism. And by a quantum system, what I mean is the following data. So firstly, I want a C-star algebra that has the space X as the boundary of its trace space. So what I'm trying to do is I'm just going to take this topological dynamical system, and then I'm going to transport it to the boundary of a suitable C-star algebra. And so everything is happening in the C-star algebra on the boundary of the trace space, and then I'm going to look at what's happening upstairs. That's what I'm going to tell you. Okay, so I start with this C-star algebra that has the right trace space, and then I want to lift the dynamics as well. So I want there to be some endomorphism from the of the algebra itself, such that at the level of traces, it is the map that I start with. Okay, and then I'll take if I take the cross product of A by this endomorphism, I will refer to that structure as a quantum cross product. All right, just one note here is that let's say that H is in fact not a continuous map, but a homeomorphism. I still need to allow for the fact potentially that the lift alpha X is just an endomorphism, not necessarily an automorphism. Okay, this pops up unfortunately. So that's why I'm taking cross product by the natural numbers, not the integers. Okay, if this alpha H, this lift is in fact an automorphism, it just is the cross product by the integers. Otherwise, it's a suitable corner of it. Right? Okay, but that's just a technical point. It's not. Yep. Yeah. I'm not even at the moment assuming that it's unital, because it's often, as I'll show you on the next slide, it's often useful to consider non-unital things as well. Okay, so that's what a quantum cross product is. Why am I calling this a quantum system and a quantum cross product? Let me sort of justify this to you. So, okay, I started with a dynamical system, and then I have some collection, some space of observables of that system, And then from this, the system and its observables, I build some structure. So classically, I'm starting with this dynamical system XH. My space of observables of the system is just C of X itself. It's continuous functions on X. Okay. By the way, C of X fits the bill upstairs. So AX, so in the definition, I say that this quantum system should consist of C star over AX, such that the boundary of the trace space of AX is X. All right, but as I already mentioned, C of X, it satisfies this. The boundary of the trace space of C of X is X. Okay, so this is allowed. So a classical system is a quantum system, as I've defined it here. And then the structure we're building that is, again, we know that this map from X to X, dually, it gives a map H star from C of X to C of X, and that's my endomorphism alpha H, right, in the classical setting. And then I take a cross product of this structure. But what I'm doing now is, instead of my observable space being C of X, this commutative space of functions, I have a potentially non-commutative space of functions, my C star algebra A, which could be something very non-commutative, which is observing the dynamics on the trace space via this evaluation, the map from A to alpha of A. And then so it is in this sense that I have a potentially non-commutative space of observables. That's what the word quantum is doing here. And this is, it's, you know, blame Riefel if you have a problem with it. It's not my, okay, anyway, so that's why I'm calling these things quantum systems and quantum cross products. Let me, so what I'm ultimately going to do is tell you that if I have some Lipschitz structure on A and I take one of these quantum cross products, I can pass the Lipschitz structure to the cross product. But first, let me try to convince you that even without this notion of a quantum cross product is a useful thing to have, because it's a way of giving you dynamical presentations of certain classifiable C star algebras that are not otherwise obviously dynamically presented. So, for example, this theorem that I'm claiming to you is that every Z0 stable classifiable C star algebra is stably isomorphic, so isomorphic up to tensoring with the compact operators, to some quantum cross product associated to a minimal zero-dimensional system, right? So you give me a Z. Okay, first I should say what. All right. So Z0 is likely not a C star algebra you've encountered unless either A, you're very deep into the weeds of classification, or B, you have a very good memory and you remember me telling you 3 years ago that this is the Frese limit. But anyway, so these Z0 guys are stably projectionless. They're very non-unital, okay? But they're sort of still, when I say Z0 stable classifiable, I mean what's called continuous scale. No, I said stably isomorphic, so I don't even need that. But okay, forget I said that. All right. So they're non-unital, but they're sort of, this theorem can be reduced to non-unital, but not so badly behaved, like not so non-unital. So I'm saying this because in the very beginning in the structure, like a unit was there, but now suddenly I'm telling you about non-unital things. I'm just saying it can be made sense. It's not such a big stretch to include this into the description. Okay, I think that this is not the end of the story as far as this construction goes. More C star algebras can be described in this way. I think it's just the stably projectionless guys are particularly nicely suited to this kind of analysis because, well, even more specifically than stably projectionless, Z0 stable ones. So what is nice about Z0 stable algebras in this context is that they have trivial tracial pairing, meaning that, so these guys can have arbitrary K0 groups, and they can have arbitrary trace space, but traces kill K theory in this setting. And that's nice because that means I can just sort of treat traces in K theory entirely independently, and I don't need to worry about the way they pair together. And that's to prove a theorem like this outside of this setting where I have to worry about the pairing, things are much more complicated because I suddenly have to take into account that as well, and I don't really know how to do that. just further on this point of things behave nicely in the trivial tracial pairing setting, one of the subtleties, the sort of annoying things about Riefel's quantum Gromov Hausdorff distance is that for C-star algebras, if I have two C-star algebraic compact quantum metric spaces and this Riefel distance is 0, what you know is that the structures are isomorphic as or unit spaces. But that does not mean that the C-star algebras are isomorphic as C-star algebras. Okay? So to rectify that, you either need to do what Frédéric Latremollère has been doing in his extensive work, where you include some kind of Leibniz property into the quantum Gromov-Hausdorff distance, and things get very, very, very complicated. Or, and I think this is a point of view that's getting back into fashion, is something that David Kern Han-Feng Lee did, is you need to incorporate into this distance the matricial structure of the C-star algebra. So you look at the structure as order systems, in other words, or not order systems, order, there we go. Thank you. Operator systems, right. Thanks. Yeah. So in the setting of Riefel's compact quantum metric spaces, you need to do something like one of these two things. You need to consider more if you want to have the fact that distance 0 implies isomorphism of C-star algebras. Okay, but what's very nice in this setting, in the setting of classifiable C-star algebras where I have trivial tracial pairing, is that if I know that the quantum distance is 0, what that is telling me in particular is that the trace spaces are affinely homomorphic. That's what, so remember the quantum distance was defined as the Gromov, essentially the Gromov-Hausdorff distance between the state spaces. Okay, so if the distance is 0, they're isomorphic structures. And then I know that when I have trivial tracial pairing, if the trace space is isomorphic and the K theory is isomorphic, then the algebra is isomorphic. I don't need to worry about having compatible isomorphisms between traces and K theory. So I have this very, very nice thing that if I know that the distance is 0 and I know that the K groups are the same, then I do have isomorphism of C-star algebras without the need to go into all of this other stuff, all right? And so, I mean, okay, I like to think of this requirement that K star A is K star B as a kind of localization. So the K theory part of the invariant is kind of discrete, and the trace bit is kind of continuous. So if we localize at particular fixed values of this discrete structure, then I have this distance 0 detecting isomorphism on the continuous part of the structure. And so I stated this remark for Z0 stable algebras, but it more generally is true whenever I have this trivial tracial pairing things, which I like to think of as a connectedness condition. Because if you give me C of X, where X is a compact connected space, then this is also an example of a C-star that has trivial tracial pairing in the sense that you give me any two traces on C of X, then they induce the exact same state on K theory. There's a unique state on K theory, in other words, for commutative connected spaces. Yeah.
Is it easier to calculate the distance than bare hands homomorphism of the tracial space?
Probably not. No. Probably not. No. But the whole point is that this distance is giving me a way to compare non-zero situations, right? So distance being 0.05 is in principle a meaningful thing to say once I've fixed these structures on my algebras. But yeah, good question. Yes, okay. Another remark that I will make that I may get back to at the end in 3 slides time is that so far I've just phrased things for single automorphisms or single endomorphisms. I have a single H on X, and I'm lifting to an endomorphism in the algebra. But more broadly, I could think I have some group action on X, and I want to lift this to a group action on the algebra, and then I could take the quantum cross product of that, right? But it has to be said, and maybe I didn't actually say this. How do I know that such a thing even exists? How do I know that I can find an algebra with the right trace space that's not a classical example, it's not just commutative? How do I know that such an AX exists? How do I know that such an alpha H exists that I can lift this map? Classification is the answer, right? Classification tells me if I have a map of the invariant, I can lift it to a map of the algebra. Classification also tells me I have a wide variety of model C-star algebras. For example, the ones I told you about a couple of slides ago, where I have my boundaries from Riemannian manifold, whatever. So I can do this at least for single automorphisms. What classification cannot tell us yet in any great deal of generality is whether I can do that for group actions. It's not at all clear that I can lift group actions of the invariant to group actions on the algebra, except in certain special cases. If I have a free group action, then I can just lift each group element individually. This gives me a free group action. That's fine. If I have a finite group, it's also fine as long as the algebra is classifiable and UHF stable. Maybe I'll return to this point in a couple of slides time. But so, okay, I just wanted to make the point that, yes, you could make this definition more broadly, but whether it's a vacuous definition outside of these certain special cases remains to be seen. Okay, so now let me tell you about how, now I'm going to say, suppose I have on my model C-star algebra, this AX with the right trace space, I have some of this Lipschitz structure. Now I want to pull this to a Lipschitz structure on the quantum cross product. And I'm going to do this, I'm going to use the fact that in my nice classifiable C-star algebra, not only do I know that there is a lift alpha H of my map on the trace space, there's a very nice lift. There's a lift that has what's called finite Lockeran dimension. Let's never mind what that means. Let's just care about its implications, which are the following in particular. First of all, the cross product is also classifiable. Secondly, I know exactly what the trace space of the cross product is. It's just the alpha invariant traces on the algebra that I start with, which is, by construction, the H invariant measures on the boundary. So remember, X is the boundary of the trace spaces, okay? So the trace spaces on my cross product are just exactly the H invariant measures of my original topological dynamical system. Nope. Nope. I don't think so. I mean, maybe we could talk after, but I don't think so. And then finally, as I said, we do get a natural way of transferring the quantum metric Choquet structure. So let me tell you how that works. All right, so I'm assuming that I'm starting with a quantum metric Choquet structure on A. What that means is I have a nice Lipschitz seminorm, or equivalently, I have a nice metric on X, which is just the boundary of its trace space, right? Then, as I've described to you before, I can now pass from a metric on X to a metric on measures on X, which is just one-to-one correspondence with A, with traces on A. In particular, having a metric on all measures, it gives me a metric on the invariant measures, right? Which is the space of traces on my cross product. So now I have, I would claim a natural way, describe to you a metric on the trace space of the cross product. And then I just now, in the same way, I pull this back up to a seminorm on the algebra itself, right? So it just, in one sentence, I've written at the bottom here. So it's just the same sort of procedure, okay? So metric on A gives me a metric on measures, which gives me a metric on invariant measures, which gives me a metric on the cross product, which gives me a seminorm. All right. So that's how, and by the way, this space, the simplex of invariant measures could be potentially anything. Any metrizable Choquet simplex is a possibility. Okay, so it doesn't have to be a Bauer simplex in particular. So this gives me a way of producing examples that are not Bauer. All right. So finally, the question I want to address is, right, so remember I started with some topological dynamical system, H on X, and I transported it to the boundary, right, of my C-star algebra. Now what I want to do is take my dynamics on X and vary it continuously in a suitable sense. Here's if I tell you I'm going to do this, maybe this is the first thing you think of. Maybe my H is rotation of the circle, and I am going to continuously vary this rotation parameter, right? So we know exactly what the invariant measures are for rotations, okay? So irrational rotations, they're uniquely ergodic. Just the Lebesgue, normalized Lebesgue measure is the unique invariant measure. Otherwise, if I'm rational, I have some periodic orbits, and the measures supported on these periodics are their convex hull is dense in the space of invariant measures. Okay, so but in particular here, I do not have. If I look at the way my simplex of invariant measures is varying as I vary the rotation parameter, it's not varying continuously with respect to the Hausdorff distance. Okay, so I'm jumping between points and things that are much larger than points potentially. Okay, so I don't have the kind of continuity I would like to have. So I don't have this continuity, and you know, what am I trying to do? I'm imagining, again, what am I doing here? So I'm imagining the circle living as the boundary of the trace space of a classifiable C-star algebra. I'm taking rotation of the boundary, I'm lifting it to an endomorphism of the algebra, and then I'm taking the cross product. And then by what I had on the previous slide, the structure I'm building on this cross product, the Lipschitz seminorm, I have to know what the Lipschitz seminorm of the function restricted to invariant measures is. Okay, but this is telling me that this Lipschitz seminorm is not going to vary nicely as I pass from fiber to fiber. I don't have the kind of continuity that I would ideally like. By the way, I should say it does form a continuous field of C-star algebras. That's fine. I mean, this you can prove. So when I do this procedure of just lifting fiberways, I can get a continuous field, but what I don't get continuously varying is the Lipschitz structure. Okay, that's what goes wrong here. But okay, I said yes, they are continuity points. Okay, whatever, let's skip beyond that. But let's focus now on what's going wrong here. Why does the example not work out as we might have liked? It's because I don't have a strong enough continuity happening here. So let's think about it. Suppose I have some theta and some theta primed that are very, very, very close together. Then h theta and h theta primed will be uniformly close. Okay, I take a point, I rotate it by theta or theta prime, they're going to be very close together. The same thing if I do it twice. So h theta squared will be close to h theta prime squared, right? Same up to maybe 10 trillion, but eventually they're going to get far apart. So when I vary this continuously, I only have closeness on finite sets of my group. But if I replace that by closeness uniformly throughout the whole group, then I do have the right notion of continuity to give me what I want. And this is what's called the equivariant Gromov-Hausdorff distance between actions. So here's the theorem that I'm claiming to you. So if I have a family of isometries of some compact metric space, some compact path-connected metric space that varies continuously in the sense that I described to you. So what it means is that if theta is close to theta primed, then h theta should be close to h theta primed. Yes, uniformly across the space, but also on powers. So h theta to the n should be uniformly close to h theta prime to the n, uniformly on the space for every n. It's a very, very strong condition. I grant you this, very, very strong. More on that in a second. But anyway, if we have this, then yes, I do my procedure. I think of this x as the boundary of a trace space of a blah, and I lift and I take the cross product and I look at fiber-wise. Yes, everything behaves nicely. I have a continuous field of my structures. The fibers vary continuously with respect to this quantum Gromov-Hausdorff distance. All right, but I just, in the last couple of minutes, I just want to, yeah, so I had a bit of a crisis here this morning about this theorem. So one thing you might well ask is, okay, well, you showed me the example of the circle, and it just didn't work. So what does work? What is an example of something that satisfies this? Here's the example that I had in mind, right? So I was thinking of x as the interval, okay? So, and I'm thinking of these h thetas. So h theta from the interval to interval. All right, so this is some homomorphism. So let's say some increasing, some map like this, right? So I'm thinking of this as like a piano string that's vibrating. So I'm thinking my variation of theta is I'm going to vary this curve, like this, so varying it, thinking of it like vibrating like this. Yeah, and I believe, although I'm now not 100% certain, but I do believe that this variation, it does fit the bill of being, it does vary continuously with respect to the equivariant Gromov-Hausdorff distance. The reason is that it's for stupid reasons, essentially. I mean, I have this global attracting point here. So if I do h theta to the power n, what's happening is I start at some point x, and it's just going to converge to 1. All points converge to 1. So for large powers, everything's getting shoved close to 1, except for the origin, which is what was, all right, maybe, but I think it maybe works. But another problem you might object to is, aha, I said isometries in the statement. This is not an isometry. If I equipped the unital interval with the Euclidean metric, this is not an isometry. Yes, well, past me said, it's no problem. Just go through the paper where this result I'm quoting is used and check that I thought it did, but I'm not so sure anymore. But then I had a third thought, if I'm counting. I don't know where the second thought was. My third thought was, all right, maybe let's go back to this remark. So this remark was that, yes, okay, so this notion, it makes sense potentially for other groups. But in particular, finite groups are okay. Finite groups are okay in certain contexts. If I take my model algebra, this ZX guy, and I tensor it with the universal UHF algebra, this does nothing to the tracial structure, but it allows me then to lift finite group actions from the trace space to the algebra itself. So maybe I think now this notion of trying to shoehorn some examples like this into this is not the right thing to do, because this, for finite group actions, this equivalent Gromov-Hausdorff distance is not so restrictive. I mean, because there's just finitely many elements I need to be closed on, right? And what I was learning this morning is that, yeah, there are lots of examples of finite groups acting isometrically on Riemannian manifolds. In fact, you give me a group with k+1 elements, I can find some Riemannian metric on the k-sphere that admits this finite group as exactly its isometry group. So I potentially have, so what I could imagine doing is taking some finite group of isometries acting on some space, whatever, and then I take some diffeomorphism of that space that's some diffeomorphism that's isotopic to the identity. And I'm viewing this as my deformation. So I start with my group and I conjugate it via this path of diffeomorphisms. And this gives me my continuously varying dynamics on the space. All right, so all I'm trying to tell you is that I think that maybe the better thing to do is to phrase this in terms of, let's say, finite group actions, where I do have, I think, maybe someone can correct me if I'm wrong, that I do have potentially interesting examples that do fit the hypotheses here. But okay, let me, maybe this is a good place to stop. So thank you.
Concerns, outrageous.
On trace basis
Yeah.
as opposed to states. So then I guess in the world where I'm coming from, you don't have that many quantum groups. You don't have that many traces,
Yeah.
very few. I mean, you've got the co-unit and that's about it. But a lot of the guys that we work with are can be expressed as graph-Easter algebras, which have a classification by what Soren Eilers and these people.
Yeah, this
So is-
filtered decay theory.
Is there some sense in which you could get around, I don't know, to use this classification
So,
of these things
you know,
to do what you're doing? I guess you understand.
yeah. Actually, what I was thinking in this context, well, a couple things. Firstly, is it clear that these are really the only traces, or just the only obvious traces on?
They're the only obvious traces.
Yeah.
I don't know. I don't know is the answer.
So, I mean, I did actually recently look into this, where something had been described about trace spaces. I have to remind myself. But what I was thinking might make more sense, and I've been talking with Robert Nyagu about this, is in these settings where I don't have obvious traces, but I might have obvious KMS states, which I think might be more appropriate to the quantum group setting.
Hey, absolutely. The KMS are there. Yeah, yeah.
Potentially, and I've not thought about this at all, whether this would behave sensibly, but potentially maybe the thing to do is try to look at elements in C-star algebra as functions on KMS states, because I know the KMS is what's called a simplex bundle. And at one fiber of this bundle, I have traces, and at other fibers, I have non-traces. So maybe, yeah, potentially. But yeah, definitely, I would like to talk about this more, because I would very much like to find some intersection between this and compact quantum groups, for sure.
Yeah. Where's it?
zero itself is I mean, W tensor set zero would be W. So yeah, so in fact, anything that is anything that has this property where traces scale K theory. So if you give me some K0 groups, a K0 group, you give me a K1 group, you give me a trace simplex. There exists a Z0 stable classifiable C-star algebra that has it that as its Elliott data. So it means it's a as broad a class as you like, just subject to this triviality of the pairing between traces and K theory. Ah, yes. Yeah. Oh, sorry. So this at the very beginning, AX is classifiable. Yeah, but you're right. I do need for these implications to be true that AX, the algebra, is classifiable. Yes. Yeah. Is it? I need to start with something classifiable. Yes. For the you may be right. You may be right. Yeah. I think just finite Rocklin dimension will give you this. Yes, you're right. In fact, I think it works. Well, I'm hoping it works. Yeah, I think it works not just for integer cross products, but for cross products by groups. Because in my new strategy of trying to do the finite groups, I would also like something like this second case. But I think this is true. I mean, yeah, this is true. That more broadly than just the integer cross products. I use it just for these implications. That's where I'm using it. I'm using it because it gives me the right behavior in the cross product. You could think of it as just a black box, if you like. It just this fact that I can always find a lift that has finite Rocklin dimension, because that's sort of crucial here, that I know what the trace space of the cross product is. It's just these invariant measures. If I don't know that, I don't even really have a starting point. So this business of trying to transfer this quantum metric structure from an algebra to a cross product, this has been done in the refill setting by people like Jens, who spoke in our seminar a couple of years ago, I guess, and David in Odense. But there, it's different. I mean, they're not, things are not, they don't have Choquet simplices, so things are not quite working the same way. So they need some other way of defining a Lipschitz seminorm on the cross product. But you need some kind of regularity of the kinds of dynamics you allow. My regularity is finite Rocklin dimension. Theirs is something else that's appropriate to their context.
Yeah.
Anything interesting happens, or maybe do have more properties if you start with X being discretization of some smooth dynamical system by which, I mean, I don't have a vector field on your manifold, you have a DFO flow.
So I guess, for example, it could be like billiards. You can so you have a ball moving around, hitting on a billiard table. This you can represent this as a discrete dynamical system. You look at return times to the boundary kind of thing. Anyways, I know what you mean, and yes, I think potentially yes. I have not quite nailed down how what exactly one can get this, but so in particular this well, okay, maybe we can talk afterwards, but yeah, I'm hopeful that this would be this potentially you could capture some interesting dynamics this way. I think, yeah.
Thanks.
I have a question. So the nice thing about this, as you said, is not just the fact that when it's distance 0, you get an isomorphism.
Yeah.
Because we could already do that basically through classification. But do you know anything what happens when it's a small distance? Like, do you expect particular regularity properties to be,
It's a
you know,
good-
to hold?
It's a
under
good
small
question. It's
distances?
a very, very good question. And yeah, I think I was also talking to David about this in Odense. Yeah, I don't know because of course, there is this Cadison-Kastler metric that's defined in a slightly different way. You have two C-star algebras living on some B of H, and you look at essentially the distance between their unit balls. And there you can make such statements. You know that if the distance is small, then properties of one transfer to properties of the other. I think maybe you even have isomorphism if they're both nuclei or something. I don't know. But in this setting, I have no idea. I mean, yeah, I don't know. This is an interesting question. I really don't know.
If not, let's thank him again. And next week, I will just remind everyone that the seminar is online only, and it will be Davide Del Martello from the University of Birmingham, talking about quantum cluster varieties, quiver seizures, and GDAHA. Gadaha. Okay, great. So see you then virtually.